Welcome to this design example number 2 about second order circuits. In this design example we have an RLC circuit with 2 resistors, 1 inductor and 1 capacitor, and there is a switch which will be connected to the circuit and the voltage source VM as shown here with a value of 18 volts. The question in place here is the following: design this circuit so that the capacitor voltage VC is given by this expression for time larger than 0. And we need to determine the coefficients A1 and A2, which are given in the formula. Okay, now let's start with the procedure as we did for the previous videos. Let's first determine the situation for what happens, what is the situation for before the switch is closed. So actually for time less than 0, that means actually for initial condition. Now we assume again that there is no energy stored in the capacitor or the inductor, so there is no current flow in this case, in this situation, at time equals 0 for the inductor, so that will be a 0 amps. And the capacitor voltage, since there is no current flowing and there is also no voltage applied or connected to the capacitor, that will be also 0. So these two conditions we have determined. This condition for the capacitor is necessary in the later state, so I will make this, I will denote this number 1. So this is a condition, initial condition number 1. So let's move on for the situation what happens just after the switch is closed. So we discussed that we denote this by 0 plus, that means just after the switch is closed. How does the circuit look like? The circuit is actually exactly the same as shown above. The circuit, the switch will be closed, and we have the R1, we have the inductor L, and we have the resistor R2, and we have the capacitor exactly the same. So we would like to know in this situation what is the capacitor voltage just after switching, what is then the inductor voltage or the inductor current. That might be also necessary, so let's write it down for this circuit also. And we have also this node X to denote that there is a node for the for setting up the equations. So let's start with the Kirchhoff current law at point X. What is that? And there's the inductor current. Inductor current at 0 plus is equal to the current through the resistor R2, that's actually this current, which will be of course the voltage across the capacitor divided by the resistance R2. So we can use the Ohm's law directly, and we have of course the current through the capacitor IC at 0 plus. So that's actually also the situation here. Now we know there is a formula for the capacitor voltage as a function of the derivative of the capacitor. We have a formula for the capacitor current as a function of the derivative of the capacitor voltage. So we can substitute that here, so that we have an expression with capacitor voltages only, and of course this is also here, so we can use it later on. So let's do that. So what is the situation here? IL at 0 plus will be VC at 0 plus divided by R2 times of a plus C times the derivative of the capacitor voltage evaluated at 0 plus. That is actually the situation here. Now this is very interesting. I also need this part of the equation to come up with the second initial condition. So I will also write that down. So let me move a little bit to the right. So what do I have? I have the following. I can rewrite this such that this is expressed as shown, and it will be IL at 0 plus divided by C, and then minus VC at 0 plus divided by R2 times C. So what I did is I place this to the left and I divide everything by C, and I get this expression. How do I determine the value of this? So then I have to use the continuity condition. What is the continuity condition? The capacitor voltage cannot change instantaneously. That is also true for the inductor current. So what I can use is the following. I can say the inductor current at 0 plus must be equal to the inductor current at 0, which is 0. We also have the capacitor voltage at 0 plus, which is equal also to the capacitor at 0, which is also 0. So if I use these two values, these two conditions here in this formula, what do I have? I get the following. The derivative of the capacitor at 0 plus will be 0 divided by C, whatever it is, it doesn't matter now, because you do 0 divided by something, minus, again 0 divided by R2 times C, and it will give us 0 volts per second. And it is actually one of the second initial value, initial condition, so I will use this later on in our final formula. Okay, so I have both of them, the initial condition 1 and initial condition 2 for the capacitor voltage. Okay, let's move on. What is now the second step in the analysis? The second step in the analysis is the force response. I would like to know what is the situation for the force response. And as we know, as we discussed in the previous examples, for force response we assume that the switch is closed and the circuit is running for a long time. So there is also again at the steady state condition in the circuit. So I will make this force response and I make this condition very clear that it is the final condition or final value. So how does it look like? What's the circuit? What is the configuration? What do we have is the following. We have the VM again, but the inductor is modeled by a short. We already know that, we already discussed this. And we have the capacitor, which will be modeled by an open circuit. This is the situation we have dealt with in the previous videos. We denote the capacitor voltage at infinity means the steady state value of the capacitor as such. And that means actually the following. The capacitor voltage at infinity means actually the voltage across the resistor R2, and we can determine the resistor voltage of resistor R2 using voltage divider rule. That means R2 divided by R1 plus R2 times the VM. Okay, now the question comes, what is this? What is the value of the capacitor voltage at infinity? Now you can use the formula for the capacitor voltage which is given here in the design example question. Now if you substitute here infinity, or you little approach the infinity to mathematically correct, then the second and the third term will disappear and you'll get only 6. So that means actually the following. You will get, since this is from the formula is 6 and this is also true, R2 divided by R1 plus R2 times 18, because that was the value of the voltage source. Then I can write the following. Using these two, I can set up the following equation. R2 divided by R1 plus R2 times 18 will be 6, and this will give me the following. Relationship that R1 is equal to 2 times R2. And I will use this. It will be denoted here as equation number 1. So we have a relation between the resistor 1 and resistor 2. That is interesting. Okay, let's move on. Now the next step is the natural response. And for natural response, we use a circuit as shown here, but we disable the voltage source. So that's actually the situation. So I can again use the same circuit. Let me copy it from this side. So I will write down natural response, because from the natural response we can determine the differential equation, the second order differential equation. Okay, so let me write it down. I will get this here and remove the stuff I don't need. So that's actually this one. This will be short. and everything here actually is as a function of time and not specifically at 0 plus. So let's make that also clear. Okay, so this is at time. This is for the inductor current, and this is also not really necessary, so let's remove this too. Okay, what do we have? Again, we can set up the equations for Kirchhoff current law and Kirchhoff voltage law. So let's make the Kirchhoff voltage law first. What do we have for the Kirchhoff voltage law? You can start here at this ground node and make the loop outside and come back to the ground loop after the capacitor. So what do I have? I have the following: R1 times the inductor current, that is the voltage drop across the resistor R1, times the VL, that is the inductor voltage, is equal to the capacitor, plus the capacitor voltage, that will be 0. Okay, that's actually the situation here, and that's the condition for here. I make also the substitution for VL, because VL is equal to L times the derivative of the inductor current, so I will also use that. So let me write it down right away. So this L times the derivative of the inductor current, and then plus the capacitor voltage. I will leave that because I am working towards the capacitor voltage. Okay, that's the situation here for the Kirchhoff current law. I will also set up the Kirchhoff voltage law. I will also set up the Kirchhoff current law at node X. That will be IL is equal to the VC divided by R2 plus C times the VC, the derivative of that. It's actually the formula we already know. So this is the current of the capacitor. What shall I do now? What is the possibility now? I will denote this as equation number 2, and I will denote this as equation number 3. I can now substitute 3 in 2, such that I have only VC and the constants of the components in the equation of the differential equation. Now, if you do that, well, you get the following. I will begin at the left side. So you look at the following: R1 times the VC divided by R2 in parentheses times C times the derivative of the capacitor voltage plus L, and then a derivative of the inductor current, which is equation 3, so I will substitute that. So VC divided by the R2 plus C times the derivative of the capacitor voltage, and as the last term VC, and this will be 0. If you simplify this, it is possible. You need to take some steps, and the final result, without going too much into detail, you can work it out very easily by yourself, is the following: the second derivative of the capacitor voltage plus, of course, if you get another term, which is the first derivative of the capacitor voltage, that will be the 1 over R2C plus R1 divided by L times the first derivative of the capacitor voltage, and then R1 plus R2 divided by R2 times the capacitor voltage. Now we have a situation of a second order differential equation. As you can see, everything is in VC's, and we have constants, and that's actually the required differential equation. What do I do now? I will transform this using the operator S, Laplace operator, into the following characteristic equation. So I will set S, which is equal to the derivative of the capacitor voltage, that will mean S squared here, and then I will have 1 over R2C plus R1 divided by L times C, and then R1 plus R2 divided by R2, and that will be 0. Okay, what do we know? What do we do next? The following is interesting to note. The equation for the capacitor, which is given here above, has two roots, -3 and -4. So we can actually set up the characteristic equation using these roots. So we have then s plus 3 times s plus 4. That's actually the characteristic equation from the formula. So I can use the following. I can say from the formula I have the following: s plus 3 times s plus 4 is also 0, and I can rewrite this like s squared times 7s times 12 is 0. If I now compare the like terms, so if you look at the two equations, the last two equations, I will equate the coefficients of like terms of s. So I will see here this has this coefficient, that must be 7. This one must be 12 here, so I can continue working towards my equation. And I see I made a little mistake here, so this must be also times LC, because I divided everything by LC. So we can move on. So this term must be equal to 12. So let's do that. So from here, what do I get? I get the following: 1 over R2 times C plus R1 divided by L will be 7, and R1 plus R2 divided by R2 times LC will be 12. And we know, let me write it down here, we know that R1 is equal to R2 times 2, or R2 times R2. That is actually also an interesting equation for now, because we can now substitute this here such that the equation will be easier to read. So this will be placed here, 2 times R2. If I place this here, 2 times R2 will be 3 times R2, and R2 in the denominator and numerator. So I will lose 1 R2, so that will be also a very easy expression. So what do I get? I get the following. So by substituting the R1 is equal to 2 times R2, I get the following: 1 over R2 times C plus 2 times R2, I mean, divided by L is 7, and I get 3 times R2. I just make it clear what I do, and it's equal to 12. So I can divide this and this, so I will get the following. I will have an expression which is 3 divided by L times C is equal to 12. Okay, as you can see, we have in this equation we have 2 unknowns, and in this equation we have 4 unknowns. So, and we have another equation here. So actually we need to select one of the unknowns to continue. So because we have too much unknowns compared to the equations we have. So let's take something, select one of the components. So I will say take C is equal to 0.25 farads. That means the following. I can use directly this equation. 3 divided by LC is equal to 12. So I can have the following then. 3 divided by L times 0.25 is equal to 12. That will mean the L is equal to 1 henries. Okay, that is actually for the inductor and the capacitor, so I already know 2 of them. Since I know the L and also know the C, I can now determine the resistor R2 here. So I can now continue by substituting the values in the equation there. So I have the R2 times 0.25 plus 2 R2 divided by 1. That will be 7. If I rewrite this, and I will get 4 divided by R2 plus 2R2, that will be 7. And again, simplifying this by multiplying the left and the right side of the equation with R2, I will get the following. 4 plus 2 times R2 squared will be 7 times R2. Okay, this is not a very complicated equation, but it is better to use a solver for calculating this. So if you solve this, solving will give you two results. The R2 can have the following value, 0.719 ohms, or it can have R2 is equal to 2.78 ohms. So it depends on the practical sense which you choose. I will choose the second one, and I will continue with the calculation of the last resistor. What do I have? I will take R2 is equal to 2.78 ohms. Then I can write down R1 is equal to 2 times 2.78 is equal to 5.56 ohms. So I have now all of the components. Let me summarize this. R1 is 5.56. R2 is 2.78. The C is equal to 0.25 farad. And I have the L is equal to 1. So let me make this clear. This is for the components. The next part is actually determining the A1 and A2. For that I need the equation, and I also need the initial conditions. So what is the equation? Let's move on. So the constants A1 and A2, that is our next step. What do I know for the equation? The equation given is this. So let me repeat that here to make the situation more clear. So this is actually the situation. This is our capacitor voltage. If I differentiate this, which will be needed for the initial value, I will get minus 3 times A1 minus 4 times A2. What do I know? I know the following. The initial value of the capacitor voltage was 0, and the initial value of the derivative of the capacitor voltage was also 0. Okay, if I now substitute here in for time 0, what do I get? 6 plus A1 plus A2. Then that must be equal to 0. That's actually what it's saying here. So I will get 6 plus A1 plus A2. That must be 0. This means A1 plus A2 is minus 6. Okay. And again, I will do the same thing here. I will substitute here. I forgot the exponential terms here, so let me rewrite this again. So this is actually minus 3 times A1 e to the power minus 3t. I was too fast by filling in the time. So it is done 4 times A2 times e to the power minus 4t. So what do I get? If I substitute here in the 0 for time, I will get minus 3 times A1 minus 4 times A2. That's actually the situation here. So I will get minus 3 times A1 minus 4 times A2. That will be 0. Now I can rewrite this formula in this form. So I can say A1 is equal to minus 6 minus A2. If I now substitute this in this formula, what do I get? Let me continue with blank. Then I have the following: minus 3 times minus 6 minus A2 minus 4 times A2, that will be 0. Now simplifying this will be 18 plus 3 times A2 minus 4 times A2 is 0. And you will get, if you do this correctly, that A2 will be equal to, let me check it for to make sure it's 18 plus 18. Okay, then you have actually the value of A12. What is this? Thus the A1 must be equal to minus 6 minus 18 will be minus 24. So that's actually the last one. Okay, now we have the complete solution, because the complete solution with the coefficients A1 and A2. So we have the 6 minus 24 e to the power minus 3t plus 18 e to the power minus 4t, and it is in volts, and it's for time larger than 0. If you want to check for the conditions, you can substitute for time equals 0. You will get 6 minus 24 plus 18, and it is actually 0 volts. So that is actually the check for the initial condition. And if you differentiate this and again substitute for time equals 0, you must also get the 0. So that's actually also a check you can carry out by yourself. Let's look at the graph. How does the graph look like? It's also very interesting, because it will give us some more insight. So this is the time, this is our voltage across the capacitor, this is 0, this is 0. So that's actually the situation here. Okay, if I draw this and I make the curve look like this, why does it look like this? Because it is an overdamped system. Why is it overdamped system? Because we have two roots which are real and distinct. So they are not the same, and they are not complex, and they are not they are also not on the imaginary axis. So we have a situation for overdamped system. So then we have the value, which is the final value, will be 6, and this final value will be reached for 99% approximately at 2 seconds. So if I make this seconds, I will have approximately after 2 seconds I will reach approximately 99% of my final value. That is actually the situation for this design example. So what we have determined in this design example is the component values of the RLC circuit given, and also the coefficients A1 and A2 of the given formula. And that's actually the whole procedure. I hope this again clears things for you and makes the calculation easy to follow step by step. So if you have any questions, comments, feel free to ask me in the comment section of this video, and I will try to answer them as soon as possible. And good luck, and thank you very much for your sharing and liking this video, and see you next time.